So yeah, hey, I'm Dan. As Lorenzo said, I'm a PhD student here, and I'm in Story, which is over there. Essentially, I used to do a PhD that looked at data acquisition for deep sea statistics, but then I got put off for some reason. So now I do computational statistics. But anyway, I'm not here to tell you about that today. I'm here to talk about GPs. So what's a GP? Well, imagine you've got a function that you want to optimize, and you don't know what this function looks like. You don't know what the gradients are. So what can we do? So we want to find the true optimum that's here. Well, what we can try and do, maybe a good thing to do, would be to try and observe the function at some points. So we're going to observe the function at some process up there. And then what we're going to do is try and fit a model to the points. We'll discuss what model that will be in a second. But then what we're going to do next? What would be a good thing to do? What we could do is draw a sample from this model and look at the minimum of that. Is that a good answer? And it turns out it is. So if we look at the minimum here, which is the green star there, if we went and acquired the data from that sample and condition on it, we get a new model. And it looks like we're getting like a closer fit, maybe a bit more uncertainty reduction closer to the minimum. But if we repeat this process again, so we sample now at this green star, which is the new minimum of the new sample drawn from that function, and keep repeating the process, we get something that looks close to the minimum. So essentially, what is this model? Well, this model is a Gaussian process. And really what a Gaussian process is, it's just a distribution over functions. And the golden rule is that the idea of the process is that if you were to collect any finite collection of points and query the function at those points, then it follows a multivariate Gaussian distribution according to some kernel. And any constraints on this kernel, that has to be a positive definite function for the multivariate Gaussians to be well defined. So to look at this a little bit more, so there's different types of kernels. So this is one type of kernel. It's called the exponential kernel, which is quite a smooth kernel. So it leads to very smooth, infinitely differentiable samples. So all these are samples from the GP, and I'm just sort of making them move along a little bit. If we look at different correlation structure, this one's called a Matern. This one's more rough, because what happens here is that the correlations between points, they decay a lot faster. So if function values are less correlated over shorter distances, then you get more jaggedy sort of lines. Whereas if you increase the distance a little bit, the points are correlated, then you get something a bit more smoother. So interesting for a GP, the multivariate Gaussian stuff is only just for the output. So the input can be anything really. So from a torus to modeling things on like the Earth, like you want to model vector fields and stuff. Or you could do sort of interesting topic modeling stuff on graphs. But also quite cool, you can model stuff on a dragon too. So here you conditioned a data point right on the nose of the dragon, and you get a new model. But anyway, this leads me to GPJax. So what we wanted to do with GPJax is provide like a library where we can teach people about these processes. And we wanted to build something that's intuitive and something for JAX. So I'm sort of joined by these wonderful people. So what we have like a weekly or bi-weekly meeting where all these wonderful people check in and come up with new ideas for improving the library. So just show you a bit more. So our library is over on GitHub. So yeah, you can fork the library and install it, or you can install it via pip, which you'll see in a second. We've also got a documentation at docs.jaxgaussianprocesses.com, where we have loads of tutorials and notebooks. So essentially, our library is designed to fit into this JAX ecosystem. I'll discuss a bit more about how we achieve that, but just to give you some more insight to what else is in the ecosystem, you have a neural network library called Flax. It's the most popular in JAX. So this is what this looks like. And to kind of show you how this is kind of functional in a kind of way, is that when you create a neural network model, so here they've created an autoencoder model, you'd initialize some sort of state, and this gets passed around. So this state is immutable, but it gets passed around. So you apply it to your model to get some predictions, for example. Another take on this is closer to how we do things in GPJax, is to have the state on the model itself. So this is another neural network library called Equinox. It's also very popular. So here you'd store variables. So this is a linear layer of a neural network. You'd store variables on the model, and this gets passed around as the state. Also in the ecosystem, you've got blackjacks. I know we've got a couple of people. Yeah, developed this. This is a really lovely library. So yeah, if you're getting into JAX, I really recommend using this library. It's absolutely brilliant. And then last but not least, another really helpful library is Optax, which is developed by DeepMind. So DeepMind have like a broader ecosystem of JAX libraries. I'm not really going to dig into all of them, but this is quite a popular one for optimization. So for instance, they provide things like the Adam optimizer, amongst others. So they focus on these gradient, mostly first order methods. And just to give you a little bit of a flavor, and this kind of looks again, is that when you're doing optimization, you're passing around a state. So each time you'd pass through some sort of gradients you've computed and the current state of the optimizer. And then you'd get a new optimizer state and then some updates to apply to your parameters. So yet again, you've kind of got this kind of state kind of thinking. But anyway, enough of that. Let's get back to GPJax again. So we kind of just have three main goals for GPJax that I want to talk about today. So goal number one is we want to make the mass representations quite close to the code, for both for like teaching and both for making it extensible and easy to do research. So for instance, I've got some code in GPJax here. So here we've got like a mean function and a kernel with like two things to specify, define a Gaussian process on. And here we can just create a Gaussian process prior, and we can create a likelihood. And we define a posterior in GPJax by multiplying the prior with the likelihood. So in a way, it tries to mimic this sort of maths, where we define a kernel, so that's this RBF kernel, where we define a prior by passing this kernel, and remember we had a zero mean function, where we define a Gaussian likelihood, and then we sort of say, well, the posterior is the prior times the likelihood. So that's kind of the take that we've taken. So sort of show you a bit more. I've got a regression notebook example to show you. So this is, so I've posted on the Teams and in the chat a link to this. But you can run these notebooks yourself if you want to on Colab, and these are over at my GitHub account. So I'm Daniel-Dodd, and you'd look for GPJax workshop. But you should be able to click on the notebook, which will be the first one with regression, and you should be able to open this in Colab. Where you can have a play around. So I'm going to run them locally. So I'm just going to start off by just importing some stuff. None of this is really that important, but the only thing I would sort of say is quite important is this line here. So unlike, so Jax by default works in float 32, but here we're using float 64. The reason why we're using float 64 is because of Cholesky factorizations. Unfortunately, yeah, it's not nice to do a Cholesky factorization in float 32. You'll get an error most of the time. So that's just a caveat at the moment, but there are other ways to solve linear systems that are underlying these sort of equations that could be run in float 32. But just to kind of show you, I'm just going to generate a data set of points. So we've got some data points, and then we've got an underlying model. And what we're going to try and do is try and infer the latent function based on the data we've seen. So the first step that we kind of need to do is we need to define a prior. And so we need to define properties that might that sort of define what this kind of function sort of look like. So we know what the function is in this case, but maybe we wouldn't in practice. But here we're just going to sort of say it's sort of smooth. And so remember, going back to the slides, that this is the first sort of kernel I showed you. It's this very smooth and infinitely differentiable kernel. So that's what we'll use here.
Can I ask a question?
Yes, of course.
There is no dimension. There is so it's just an abstract object.
Yeah, exactly. There's no data at this point. It's just an abstract object.
Okay.
So yeah, the data's going to come in a moment. So yeah, this is. So like, there are reasons like why this was set up this way. Like before, in the past, we had to like initialize a state based on the data shape. It's kind of to do with that kind of thinking. But yeah, there's no data yet. Some of these might have like dimensions they act over of the data that you might have to specify. In a more complicated modeling situation, yes, you might have to think about data shapes. But here, just more generally, like no, you don't, yeah, there's no data thinking here for the moment. So just to sort of show you, this is what a kernel looks like. All it is, it's just a data class, and all it has is this variance parameter and this length scale parameter. So if I put the variance, you get this is the default value. Show the length scale. That's the default value, the length scale. So then you also have this argument called gram, and that's to create this bit to define this multivariate Gaussian distribution. So if you call that, what return is, so in GPJax, we don't return like dense arrays, we return linear operators. This is something I'm going to talk about a bit more in a moment. but you sort of see you can return that matrix.
Yeah. So the visual dimension, right, is 100 by 100.
Yeah, once you put the data in, it is.
Yeah, because you put the
Yeah, if I change this, then it's abstract.
Okay, okay.
Yeah. So the only thing that we do like to specify, well, actually, it's going to come later. We'll look at the prior first. So we look at this prior object. So if we remember going back to the formulas, if I query my x at my f of a finite batch of points, I get a multivariate Gaussian distribution where this is the covariance. So we kind of mimic that in GPJax. If we just pass through a batch of points through the prior, we get back a distribution, and it's that multivariate Gaussian distribution here. So you could look at the location, and you see like it's a load of zeros, because remember on the prior we defined a zero mean, and if we had a look at the scale, it's essentially going to be same as that ground matrix I just showed you a moment ago, but just a little jitters added on just for numerical stability.
So can I just, where is it getting the metric on the?
I'm sorry.
Where is it getting the metric on the input space from?
The metric.
Yeah. So length scale, right, is being compared to the metric on the input space, and I've missed where that gets fed in.
Ah, yes. Okay, we'll see this a little bit more in a moment. So essentially, the object has, this is where it gets slightly more confusing. Essentially, this is not maybe fully functional, but it kind of is kind of functional. But the kind of idea is that you have a state, so which is our length scale. Our length scale equals 1.0, for example, just to say for that parameter. But that state defines the computations on that object. So if I change the length scale to 2, for example, I get a different ground function.
Right. Well, my question was, you fed in x, so it was all abstract until you fed in x. And as soon as you fed in x, you had the ground matrix, which is great. But to compute that, you need some kind of metric or distance measure on your input space. So I just assume Euclidean, or is that?
Also, yes. This is Euclidean in this case. If you're referring to the distance between the points. Yeah.
So if it wasn't, can you feed in another metric, or
I haven't set it up that way for this kernel, but yes, in practice, yes, you can easily code in your own metric and add it in. I can give an example later of that when we look at the kernel in a little bit more detail.
Yeah.
But this is the kind of general setup. So yes, we get this. But anyway, if we query the prior finite collection of points, we get this multivariate Gaussian distribution. And what we can do is we can draw samples from that by passing in a key, which is that Jax key from earlier. The only nasty thing about this at the moment is we're having to use seed equals key, because that matches the signature for TensorFlow probability, which I don't really like too much, but it just is what it is. But recall the key is just a Jax PRNG key. So you can draw samples and plot them, so that looks all lovely. And essentially, this is like what we think the kind of properties that the function we might observe sort of have sort of says. So it's going to have some sort of smoothness, But then the kind of next step is to kind of move towards constructing a posterior. And the first step in constructing a posterior is to define a likelihood. So here we have a Gaussian likelihood, which just has a noise parameter. So just to show you again, this is another data class, but just to show you, you have a default noise parameter on here. So it sort of behaves similarly to the kernel. If I'm actually to change this noise parameter, then I get different computations on this object. This object, unlike the kernel and everything, is immutable. But the only thing you have to use to define a likelihood is just how many data points you're going to use. That's just to work out shapes for later on in more general settings. And then the final thing is you just multiply the prior by the likelihood. This defines a posterior. And just to show you what that looks like, you sort of have this conjugate posterior sort of collection, which is again a data class, but you now sort of you accumulate a prior within there, and you have a likelihood in there. So we'll go through a little bit more what's going on here. But if I went posterior.prior, then I get back to the prior before. So it's like a tree structure sort of building up.
So would that work if you did likelihood times prior?
Well, on this one, you'd get a new. I think you'd get a new one. You'd get a new posterior.
No, if you did it.
Oh, I see. Yes, it's commutative. Yeah, it was a bug in early GPJax though. I grant you that. Yes.
You have to point the fact that it's conjugate with the gas, the gas.
Yes. 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 So during the multiplication process, yes, you say if it's Gaussian, you return this. If not, then we return a non-conjugate posterior. So if I change the likelihood, we look at a Bernoulli distribution as the likelihood. For example. You see, you get a non-conjugate posterior now. But so in the non-conjugate setting, you have to learn a little bit more, because in the conjugate setting, you can sort of marginalize stuff out. But you get different objects. But then, so once you have your posterior, the next kind of step, crudely, is to kind of do some hyperparameter learning, because we've defined a length scale, a variance, and observation noise for our likelihood and prior. But in practice, we don't know what those values are. So there are different ways you could do that. You could do that via MTMC, which would probably be the correct way to do it. But a hack that everyone does in machine learning is to realize that you sort of integrate out your process and to get like a marginal likelihood of these hyperparameters. So that's kind of what we're doing here. Oh, that's
Yeah,
great.
it changed back from Bernoulli to.
Oh yeah, yeah. Thank you. Yeah, so to define like an objective function in general, there's different objectives in different settings, but for a conjugate posterior, we can use this conjugate marginal likelihood to get this objective. And a negative just says that we just want to negate this function for minimization purposes. So, and what you can sort of do is you can pass through, this is where the data now appears. So you can pass through your posterior as a state to this loss function, and you can pass in some data. And yeah, you get 124 in this case. But what's kind of cool is you can take this loss function, and we can use Jax's value in grad. You can work out the value, and you also get a gradient. And the gradient is the same form of that tree before, that tree collection, but it on each of those leaves, it now has the value of the gradient in each place of the data structure. For instance, if you looked at the observation noise, that's the gradient you get against that loss function. So you return the same sort of state as before, but you get gradients at each of those parameters. In general, well, this is just a little point, but in general, because it's set up for research, we quite like to cite things. Every object in GPJax is set up with a cite thing. So you have like this dispatch cite operation. If you just chuck it on any object, it will return you a little bit of text. But for training, you could check this loss function. And then this going back to this optax optimizer that I discussed earlier, you can use that to sort of fit your model. So, because some of these parameters are defined in, have to be positive. So the length scale and the variance, I think all of them actually have to be positive. Yeah, all these values are squared values, so they all have to be positive. So when you're doing optimization, you first transform your model to the unconstrained space, and then perform optimization there. So that's what these chunks of code are kind of doing.
And here is all sequential, or you're using any sort of parallelism in the optimization?
Yeah, it's all sequential. Yeah, so I just thought I'd show a crude for loop here. Yeah, so on each iteration, we'll take that value and grad, like we did before up here with this gradient.
Yeah.
So you return like a gradient collection, and yeah, you're going to pass through this optimizer state. In which case it's the optimizer state for the Adam optimizer. So yeah, it's all sequential, but each step you're updating a state.
But the gradient calculation probably is parallel. So it was a big Gaussian process.
Yes.
Would run that gradient calculation.
Yes.
And about like the memory, because we mentioned yesterday that you should allocate things in the GPU memory before.
Like, yeah, so Jax has some various heuristics for whether it should just run on the CPU or on the GPU.
Okay.
So yeah, in principle, this will parallelize, whether it does or not. Principle.
When you unconstrained, is that like a default transformation, like one scale or something, or?
Yes, that's something we'll talk about as well. I'll show you this on the kernel, for example. This is the next one we're going to move on to. But yes, you have default transformations, and essentially they're termed as bijectors. So previous to us, there's another lovely Gaussian process library called GPFlow in TensorFlow. It also has this kind of same terminology floating around, but bijectors sort of comes from TensorFlow probability. But yes, these are like just, you could replace them with generic maps if you wanted to. But in this case, yeah, I'm just using a soft plus. But yeah, we can plot the training history of that loop. And you get something that decreases, which is great because it tells you that you are minimizing the thing. And then, yes, so recall that we passed through this loop, we passed through this posterior state. But that got updated, so we should be able to do a prediction with that, and you get something that fits quite nicely to that data. Just to show you the effect of hyperparameter optimization, if I create a new posterior, so these original prior and likelihood were unchanged because recall they're immutable, remember, and they weren't passed through the optimization loop. So there's no side effects in any of this code. So if you didn't optimize your hyperparameters, you'd end up with something like that. So it doesn't look very good. So your hyperparameter alone is quite important in Gaussian processes. Yes.
Is that just random hyperparameters that are being purchased?
That's just default hyperparameters. I mean, just say like SD5 equal to 1, or just or a sensible value in other cases. But yeah, that's the first notebook. So any questions? Okay, cool. In which case, I'm going to move on then and kind of show you how we kind of achieve some more of these things. So essentially, so our goal one was have something that's somewhat close to the maths and hopefully easy to use and to do research on. But I was going to talk about a bit more about how we kind of achieve things in JAX and how we set up things in our way. What we kind of do is under the hood, and I'll talk a bit more about, show you a little more in the next notebook example how this kind of works, is that we represent all objects, these things called pie trees. And these are these lovely data structures that JAX provides. And you can apply loads of transformations and modify these trees. But yeah, so that gives you lots of flexibility. But in addition to this, the way we set it up, we've kind of got quite an object-oriented kind of feel to the library, but we have like this stateful kind of thinking. You have to keep the state in mind. You're still using everything in a functional manner, but we have all data on the objects. So it's compatible with everything in JAX essentially. So I've already shown you models that work with grad out of the box, which is great, and all of other JAX transforms. And yeah, the secret to doing that is that we just have this base module abstraction that we inherit from, and I'll show you a bit more how that works in a moment. But before we do that, I just want to mention our third goal. This is kind of how we want to differentiate ourselves more from other Gaussian process libraries in the literature. And kind of, so Python, there's loads of good libraries that do Gaussian processes, but I think structured computation is something that's just not talked about or been developed enough yet. And I'll talk about what I kind of mean by structured computation. Well, so recall you have this rule that you have all distributions are Gaussian. If you query a function at a finite collection of points, you get this multivariate Gaussian, and it's the n by n covariance. But naively, what this sort of means is, if you were to do stuff for GPs, if you want to evaluate densities of multivariate Gaussians, you're going to end up with this cubic cost if you assume a dense array. And why that is if you have an n by n covariance, you have this formula to compute this multivariate Gaussian. So you have this determinant down here, and you also have this inverse here. sorry, naively, that's Dodd scale of order n cubed. So we wanted to sort of set up a more of a structured computation. So instead of computing this gram matrix, which is also not even needed in most a good chunk of situations, we want to compute, be able to compute potentially a sparse linear operator. So we want to kind of provide like an abstraction that sort of links where you would input your data points and you would return back a sparse linear operator. So that what you'd kind of end up doing then is working with linear operator Gaussian distributions. So like this is not necessarily like a new idea, like TensorFlow probability supports some linear operator multivariate Gaussians, but it still hasn't quite been extensively developed enough to do quite a lot of GP modeling situations. But yes, I'm going to move on to my second notebook now, which kind of shows you a little bit more how this kind of works. So yeah, so remember we have it's in the PyTrees notebook now if you're following along on the Colab. But so recall that you have it's been a running example is the RBF kernel, which has two parameters, this variance parameter and this length scale parameter. And essentially we could sort of represent this in code, something like this. And what I've done here, this is a special type of class in Python called a data class. And it allows you to write code in quite a readable manner. So I've got two attributes, length scale and variance, and I've just got a call method. So just to kind of show you what that would look like, if I created a kernel, get back a data class with a length scale and a variance. But if I were to put in two data points, in this case, they're not Jax arrays, but it's fine for this example. What we get back is the covariance between those two inputs. So like more crudely, you could represent this class, this data class through like an init method. There's quite a lot of benefits to using data classes. So for starters, you get rid of these inits, and it actually means when you start inheriting from classes, you can get rid of a lot of these inits and generate them automatically, which is nice. But there's also other benefits too. If I created two kernels, and I were to do something like this, is K1 equal to K2? Yes, true. And I think in this context, I would like that to be true because it's got the same data, right? It's got the same length scale, which is default 1. I've got the same variance, which is default 1. Makes sense. Whereas with a standard class, using it in this context, you see it's false, but it's other things as well that other benefits as well the data class adds. So it's great. So we've got the first building block of how we design this library is around these data classes, but then that's not quite enough. So if we were to create a kernel, for example, again, but we try to take the gradient against this kernel, you get an error, and the error is that this object's not a valid Jax type. That's no good, is it? I just showed you a moment ago that I could take gradients against different objects and return the same sort of forms of those objects. So actually, how do we get around this? Well, really, how you get around this is why JAX is really flexible, is you have this pie tree abstraction. So if you were to go on the JAX site, there's a really good, or the JAX documentation in general is really good, I think. But they have a really good sort of notebook sort of explaining this in a little bit more detail than we're going to go to here. But to try and provide you a little bit of an idea, just think of like a nested data structure. So one example, you might have a list where the first element is some sort of float. Then you might have like a dictionary. You might have like an object inside this dictionary and going to true a false value. So by default, JAX recognizes things like lists and dictionaries and tuples as pie trees. So like these nested data structures. So in particular, if we were to inspect the structure of this pie tree, I'm using this thing called a tree structure from the JAX.treeUtil library. And you can see that I return something that looks the same as before, but I've got asterisks where the data should be. And I could look at the leaves and recall that where the asterisks are, those are where the leaves will fill in the bits and parts. So another example, which is more useful to JAX, is kind of where maybe you've got, in this case, we've got a tuple of arrays. And in general, how JAX works is JAX, most of the operations in JAX run over pie trees of JAX arrays. So this is an example of a pie tree of JAX arrays, which have got a collection of different arrays. And what you can do is you can do fancy things like mapping over these arrays. So you can use this thing called a JAX.treeUtil.treeMap, and I can provide in a lambda expression for manipulating that array. And you can see I've squared each thing in that array, but for each thing in the tuple. So it's quite flexible, quite nice, and it's kind of agnostic to how your data is kind of structured, as long as it's a pie tree. So like another example might be your sum of squares. But yet again, this data structure, that tuple works over this because it's a pie tree. So that's what JAX grad does. So under the hood, what really happens is JAX will flatten out these trees into these sort of lists in these maps and like apply each element to like the map operator. But it sort of means that we can take this idea like a step further. So we kind of want to make a data class somehow on these pie trees. And JAX makes a nice way of doing that. You can register different objects pie tree, as long as you tell it how to flatten into a list on each level. We do this through our module abstraction on our base. So this is kind of how we rewrite models in GPJax. So here I've got my same RVF kernel, but I've got a length scale and a variance parameter. But I've got these things called param fields. And what they have is default values. And then I've got a type of bijector, it's that transformation we discussed earlier between the constrained and unconstrained space. And I've also got a trainable status for that parameter. So if I were to initialize this, And it looks like a normal data class just as before. If I were to run that gradient operation, we can see that it passes with no issue there. So in fact, we can take that away. You can see you would return now a gradient where the leaves have the respective gradients. So in GPJax, yeah, we try to write objects like this. And what this allows us to do is, if we were to constrain this object, it would apply these bijectors forwards on each of these leaves. We could unconstrain. So you can do transformations like that. But the idea is that you'd specify all the things that your parameters would have as kind of these metadata attributes like that. Is there any questions on this? Okay.
I have a question, but it's more of a conceptual one.
Yes.
And now I'm going to say that I'm realizing it might sound like a criticism.
That's fine. Yeah.
But Jax, like the whole point of it was to kind of get away from the object perspective, right?
Yes.
So why did you just like rush back and put it back into a notebook framework?
Yeah, we went back because we could write models in quite a compact way. Yes, I think there are aspects of this that are perhaps slightly over-engineered.
The trainable flag is essentially some residual of PyTorch, right? So like the GPY torch.
Oh, for which thing?
It's like the trainable flag, right?
Oh, right. Okay. Yeah, I don't know.
That's something you found in like the early work by Sheffield people, and also like some.
Okay, that's interesting. Yeah. So I took that from GP.
Kind of it got complicated.
Yes.
But when you work in Jax, like you just take gradients with respect to whatever parameter you want, right? Like you just tell it what to compute.
Yeah.
Always.
So I think I agree with you on this. I'm thinking like longer term, we're going to be removing those trainable things from this object. We'll probably, at the very least, though, specify kind of the bijector here is kind of to say what kind of domain your parameter kind of lives in. But at the very least, we'd kind of specify if your parameter should be in a positive domain or something like that. That's what we're thinking of moving towards longer term.
Why do you even need to do that? I actually understand, because it's just a function composition, right? So if I have a kernel, it's a function. I just like ask it about a function.
Yeah, but when it comes to optimization, we need to know, or computing priors or something like that. We need to know what spaces each parameter lives on. So maybe like one way around that would just to say that all the length scale should be on the unconstrained space always. The variance should be on the unconstrained space always. That'd be another way of doing it, and that would get rid of that problem.
The TensorFlow bijectors, right? They essentially are they were developed for the normalizing flows.
Yes.
Right. And so you're kind of like twisting their neck a bit and telling them like, well, telling us you're using them to implement exponentials. Right. So
yes.
I mean, as I'm saying, it sounds really bad. Like what you're doing is valuable. I just actually never understood why people just took Jab and then like went back and slapped it into an object-oriented framework. It's a conceptual question. I actually have no idea why.
Yes, yeah. I still yet to make my mind up fully of where I rest on like all the things. But yeah, I think I certainly said there's going to be some changes made to this at the very least. But essentially, what I'd kind of like for the future, I'd like to be able to take my model and then return the same structure that just says, oh, this parameter belongs in this domain, this parameter belongs in that domain. But all the operations that I apply to these models are still going to be functional. But the reason why we went for these data on the object approach is more because we found it easier to sort of build models by nesting these data structures. So it kind of became apparent that it'd be quite nice to have this kind of structure is more when we've been sort of thinking about things like adding Gaussian processes together. It sort of became harder to think about how to deal with adding different dictionary collections together, for example. This felt simpler at the time. But yeah, we essentially are following like kind of the same sort of thinking as Equinox here. But yeah, I think for other problems, I quite like having just a state of like a frozen dictionary of parameters for other problems. So I'm sort of messing around with like I kind of want to develop a little probability library, but we'll see how far that gets. Because of course I also have to do my PhD, but just because I kind of think at the moment it's kind of annoying that there's nothing in JAX that is actually functional for probability, really. Like NumPy isn't functional. Probability scoring isn't either. As an I want to, yeah, I don't know. It's just a thought.
Say for probability, like
TensorFlow probability.
oh, it's like Jack. That's purely functional. Like it's
Yeah, it's more like writing models. I guess it kind of is, but it kind of isn't. Like for the same reason, so each object in TensorFlow probability yet again has all these parameters defined on those things that define the computation of the log density function. So it's sort of doing the same sort of thing we've got, the naughty trick we've got here, right? So it's not really functional, but it kind of is. But it kind of depends on your viewpoint.
So the idea here is using the object as a way to sort of query
Yes.
over all those kind of static parameters that define the kernel.
Yes. Yeah. Exactly. Like to try and like collect them all together, and yes, as a means like we can pass it through different things. But just to make it very clear, because I don't think I did earlier. If I create a kernel, you see I get an error if I try to change any values. So everything is immutable still. But it's kind of like all the fields define the state, the fields of the data class. So remember fields were these things here. So all we're saying that these things are the state, and everything else is a function of that state. It sort of is a naughty hack, but I still think it's quite nice in certain problems.
because that's a JAX object, you can still set it like just with that set method, right? So, and even though it's functional, it's kind of, I mean, Not about your library, right? It's just about the general idea of.
Yeah, it's interesting, but this in general is literally no different. Although I imagine I imported that somehow, or I don't know. I have to worry about that at some other point. But the kind of point, it's still following like the TensorFlow probability kind of model. So I created a normal 0 and 1. When I come to compute, the log compute, I just pass in where you have a self, but if you pass in like a value, you get a number back. You're not passing in the 0 and the 1 there. So like there isn't actually anything that functional yet in probability in Jax, I guess. So you start creating an object, but this is no different from that, essentially conceptually in my head. But maybe I'm wrong. But just kind of show you like where this sort of idea sort of goes on to. Imagine just like trivially here, like you got something quite simple, like a white noise process. The white noise process just says the points x and y are correlated if they're equal to each other. Otherwise, there's no correlation between those 2 points. So essentially what that means is we took a kernel, we made a white noise kernel. So I'm just going to create like the x equal to I again. But if we were to create the gram matrix just naively, you can compute that as like a dense array. But kind of what we do in GPJax instead. So here in this gram thing, we're just using something called a phi map. I don't know if that was discussed earlier, but that's where you sort of vectorize functions over arrays to do. In GPJax, we do something slightly different. Now we have we're still working on this. It's very much work in progress, but what we kind of have is this compute engine. That's what we call it, and it's to sort of do the gram matrix computation. So like by default, you'd have something called a dense computation engine, and you'd create that dense array, but you'd wrap it in a linear operator. So we're using this library called Colab, and I will show you a little bit more about that on GitHub in a moment. But essentially, it's just a recent collaboration we set up with essentially the structured way of doing it for this process would be, instead of returning a dense array, you'd return a diagonal linear operator, right? So it's going to have the same kind of properties as an array, but it's now a linear operator. So what we do on the kernel is we define a compute engine that defines the computation that should be used, which could be overridden in cases of approximations. But all the kernels are always like one-dimensional calls. So you always consider, in GPJax, you just consider what's the covariance between 2 points, and to return that single number as a one single dimensional array. But then you have a gram that would go to this compute engine and do some sort of vectorized operation on this. So in the case of the white noise, this gram returns a linear operator. It's a diagonal linear operator in this case. So here I printed it out and that's what it looks like. And if I made it dense, then it's the same as before. But why it's kind of beneficial is if we multiply it against some points, I don't know if it's going to be a big enough example, but maybe we get interesting. Well, maybe that's a bit bigger example, but in general, it will scale better. I might have just made an error somewhere, but
You've forgotten the block.
oh yes. Oh, sorry.
So like this is you're actually not computing anything there. So you have to like put a parenthesis on dense at x, and then like add the method block until ready. Yeah, and the same result. So otherwise it just return futures.
Well, thanks for that.
So this wouldn't keep the whole matrix in memory.
No, it just stores it still just stores the diagonal component. I guess it's just a bit more overhead on just that simple example. Maybe I made this massive. Otherwise, there's a bug in their library. I'll have to have a little look. Okay, well, it's starting to get better, but I think, yeah, there's additional overhead for having the class there, but yeah, in general, I think at least what you'd hope you'd see is that this would scale linearly in the number of data points. Oh, sorry, yes, this one, the structured one would scale linearly in the number of data points, it's a diagonal matrix, whereas the dense one would scale, yeah, quadratically. For this matrix multiplication. But that's kind of the structure that we kind of like to exploit. But kind of importantly, that we can just sort of use the same code as before, but just replace the computation abstractions. So we don't need to create new objects for a diagonal case of a GP or a new case for a Kronecker case of a GP. We can sort of use the same code, but just replace a computation abstraction. That's the kind of idea anyway. So yeah, just to show you just a kind of bit more, that's yeah, so just to finish up a bit more, that yeah, we set up a collaboration with this library called Cola. It's quite a new library. It's come out of Andrew Gordon-Wilson's group, and yeah, it's quite nice. They provide lots of different linear operators that you can use. So it's a library that's written in both JAX and TensorFlow, but quite nice is it provides loads of iterative solvers as well as actual recipe factorizations, etc., etc. But anyway, that's pretty much all I wanted to talk about. Does anyone have any questions?
Can you have a multiple output? So, I mean, these are all defined like, you've got maybe like a 2x2 space and it's that function, it's one thing, and use for that function. Down the kernel sort of define what coordinates, etc.
Yeah, so this is something that's under active development right now, and we're working on a clean way to do this. So kind of different answers. So answer one, like you could get multi-outputs by extending your input space. So if you went from, you had some outputs, maybe y has like 1, 2, 3 dimensions. Maybe these are different indices I, but what you can sort of do is you can just extend your data points to ix. That's not like computationally efficient or anything, but it's just like one way you can sort of pack it in for the moment. But then recently, yes, we've added in a co-regionalization Gaussian process. That's very recent over the weekend, someone wrote that in. But yeah, longer term, that we're looking to be able to set up neat computational abstractions to deal with that vector output. Because I think we need to rewrite a better Gaussian distribution to deal with those tensors. You kind of need to flatten things out perhaps and then reshape. That might be one way to do it. Or to kind of think about how you can structure that somehow. So it's ongoing thinking, and yeah, it's something that I'd hope we have like a good answer on over the next few months. But it's the next big thing we want to work towards.
Any other questions?
Yes.
What do you actually interface with for the optimization bits? Because you were talking about Bayesian optimization at the beginning.
Oh yes.
Like GPJax has full torch. What do you have?
So at the moment, so this is something that's under active development, not by myself, but it's sort of led by Henry Moss, who's involved with the library. So very recently, there's been some development of this decision-making submodule within our library. So essentially, this is sort of following, it's taking some elements from PyTorch, but mainly from Trieste, which is kind of the project that Henry was involved with previously. It's very crude, but it's an ongoing development. But essentially, similarly to Trieste, that you sort of build up like different evaluators to sort of evaluate different data sets and get them into like a dictionary form, and then you've got abstractions for search spaces. It's sort of following that kind of design. So the only thing that we kind of have at the moment is we support Thompson sampling, but we hope very quickly that we can get other acquisitions written into the library. But longer term, that perhaps we might have a GPJax library. I own the name on PyPy, so it could happen.
Any other questions? If no, let's take down again. So we are taking a break of about 15 minutes, I would say. Then we have Sebastian. Hopefully, coffee is outside. Very nice. I finally know something about collision processes.